Welcome back to another lecture on speech processing. So last class we were talking about the importance of recurrent neural networks as opposed to deep neural networks. The idea is if there is a sequence of events happening, then you can capture that information and use that context to do something more better, right? That's the whole idea. And one of the applications that we started discussing last class was this concept of language model, right? If you recall, what does a language model do? Language model essentially is trying to find the probability of a given word given some previous words, right? So given that I know previous 2 or 3 words, can I predict this word? Okay, and that's that's sort of the concept that's also used, as I mentioned before, when you want to or when you want to autofill, right? So it could be at the character level, it could be at word level, whatever it is. So the idea is that when you're typing, it tries to fill the word, right? Finish the word, right? Or when you are trying to do search on the Google or something, it tries to give you the next few words or something, complete the sentence, right? So all of those are basically based on the idea of language models, and these are actually learned, right? With a huge amount of data, we try to learn. These are all text processing, right? So you're using text data to do the processing, right? And why is language model important? So if you remember the conventional speech recognition problem, which is converting speech to text, has 3 components. What's called the acoustic model, which consists of the HMM and the GMM. Then there is the lexicon. So the acoustic model will give you, given the MEL filter bank features, a sequence of phonemes, right? From the sequence of phonemes, you create words by looking at a lookup kind of dictionary, which is called the lexicon, and then we try to find out which is a meaningful set of words, right? So for example, if you look at the sentence, it's fun to recognize speech and it's fun to recognize speech. They have almost similar set of phonemes. So the words, now the 2 sentences are, it is fun to recognize speech and it's fun to wreck a nice beach. Okay, so both of them have actually similar sounding phonemes, and therefore the acoustic model is not a big help. It is the language model which sort of says, well, this sentence, it is fun to recognize speech, is more commonly used. It's not very rarely in that whole text that you use to build the language model, very rarely it would have seen an event like it's fun to wreck a nice beach. Okay, therefore it will give more probability to it's fun to recognize speech and output that, and they are always bound to make mistakes. There might be occasions where you might have said it's fun to wreck a nice beach, in which case of course acoustic model also will sort of improve for the wreck part of it. So it all depends on the weighted average of the acoustic and the language model. If it finds that the recognized speech is better, it might choose this even though it might be wrong, right? So all systems make mistakes. A good system makes lesser number of mistakes. That's the whole idea. Okay, so the whole idea of language model is to predict another a word given a sequence of previous words. So for example, if I have the context the cat, then chased will have some probability, sang will have some probability, smiled will have some probability, all of which is found by counting, right? So we find the number of counts when the cat chased occur in 3 consecutive words divided by the number of times the cat count occurred, right? So this is the language model, and as I said previously, to have even contexts which are 5 words away or 4 words away is very, very difficult in the count based methods. So we have to use something called discounting, the smoothing, and so many hundreds of things that we have to do. Okay, so there is an alternate approach, which is the neural based approach. And so in the neural based approach, what happens? We are going to use recurrent neural networks. So this is one of the first big applications where it really made a big difference. So RNN language models are extensively used nowadays, and the basic idea in RNNs is that you have this cross kind of path which sort of captures the context and sends it to the next guy. So if I have the start of a sentence and it has to predict the output of start is also fed to the next word, which is the, and the output should be cat. So, the cat chased and the cat chased. What is the purpose of language model? The purpose of language model is to predict the next word. So, if I give start and the, it should predict cat. If I give start the cat, it should predict chased, right. That whole sequence is going from left to right and is actually passing through these connection from one input to another input through this output of the previous layer being fed again, right. And that is the whole idea of recurrent neural networks. And we saw that this is a very good way if you have long sentences. So, for example, I grew up in Assam where I went to school and therefore I speak fluent Assamese. Assamese actually depends on Assam, which occurred many words back. Okay, and this would be requiring like a 10 gram or a 12 gram and an n gram language model. We cannot do that complicated or that big context, right. We can never find counts where exactly such things, it might only occur once or something. So, it is not a good estimate of what we want, and therefore, this recurrent neural networks were powerful. They were able to capture such kind of long context, and they really helped the field of language modeling grow a lot. Okay. And of course, I also mentioned something about this idea of LSTMs. I do not know if yeah. So, the problem with all this recurrent neural networks is there is some kind of a decay as we grow go through the network, right. And therefore, you have this problem of vanishing gradient or so if you recall, I talked about when you adjust weights, we need the derivative of the error with respect to the weights, the partial derivatives at least, right. So, and we use chain rule if you have if you want to go across to a weight that is quite inside, right. Now, because of this, the gradient gets smaller, could get smaller and smaller and smaller and almost becomes 0. If it becomes 0, the weights are not going to get updated. So, the there is no update, right. So, then the neural network is not learning, it just stops learning, right. Or if it becomes very big, then the neural network is going to change the weights all over the place and the training also will not happen properly, right. So, therefore, this idea of LSTMs are used in recurrent neural networks. Now, I am going to today talk about this idea of how are we going to represent words, right. So, you remember words are something that you have some letters and all this, right, but the recurrent neural networks need some MFCC like Melfetta-Bank features or MFCC vectors, some kind of a vector with some real numbers, right, so that I can do some operations on the computer, right. Now, therefore, I have to change this the word to some kind of a vectorial representation, some kind of a vector, a number of numbers, and similarly cat should be one kind of vector and so on. So, now how do we change this, right? So, that is what we are going to discuss today. Okay. So, I have the recurrent neural network, right. So, so we have this paths that are going, right, and then we have this U, and then the cross paths are there, which is the W, right, and this is again let me put it as V, right. So, if it's this is start of a sentence and that's the symbol that I have to give, then I give the here, cat, then cat comes, chased, the, right. This is how I am going to predict, right. So, now these are words. So, how do I represent words? How do I give it as a feature vector, some kind of a feature vector, some kind of a vector that is going to be as input. Remember, here I am predicting. So, here it will be the there is actually some kind of a softmax and I am going to predict so the among all the words. So, let us say there are 100 words, right. So, this will be 100 cross 1 probabilistic vector that will come, and one of them the part will tend to 1 and all the others I will tend to 0. So, that is how I want this output. Similarly, this guy will be for cat somewhere here and that will become 1 and all the others will become 0, right. So, that is what we are going to do, right. So, this is the output. Here we are going to, why are we doing this? Remember, the softmax gives you like a probabilistic. So, this is a 100 class classification problem where we know one of them is correct and all the others are not correct. So, the one that is correct I will put 1 and all the others 0, right. So, now people got the idea. Here also I can do a one hot representation. What does it mean? So, in a one hot representation, let us say I have only 6 word vocabulary, okay. So, that means only one non-zero value, that is why it is one hot, only one of them is non-zero like this, right, and all the others are 0, okay. Okay. And so, this is called a one hot vector. So, the way we do it is very simple, right. So, suppose I have 6 word vocabulary. There is nothing else that I have, okay. My whole language has only these 6 words, right. Data science, cool subject, something like this, right. So, now I can simply say in the first word I will put 1 and put all the other zeros, okay. So, this is a 6 cross 1 vector representing data. Similarly, for the next one I will have 0, 1, 0, 0, so 2, 4, 5, 6. This is a word for science. The third is 0, 0, 1, 0, 0, 0. This is for is, right. So, this is also 6 cross 1. Then 0, 0, 0, 1, 0, 0. Then 0, 0, 0, 0, 1, 0. And finally, 0, 0, 0, 0, 0, 1. Okay. So, this is called a one hot representation. For a 6 word vocabulary, we have a 6 dimensional vector with only one of them being unity and all the others 0. Okay. So, this is a one hot representation. Okay. So, for example, you know, if I had only 3 words, right, say apple, orange and man, right, then what will I do? This is a 3 word vocabulary, right. So, then what will I do? I will say arbitrarily one of them I will choose 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay. This is a 3 cross 1 vector and this is also one hot representation. Okay. So, this is also one hot representation. Okay. So, therefore, this is one thing that people started using, right. So, once I do that, it is very simple, right. So, I instead of my MFCC or Bell filter bank, I am going to give a one hot vector here, right, and then I will do it, and so my problem is solved. So, my only problem with using words was how do I convey words to a computer, like in what way will I convey it, and so the idea is just use one hot vectors and it is you know, useful, right, and this problem can be solved, right. But there are issues. Suppose normally I do not have a 6 word vocabulary, right. So, even in everyday conversation we use 2000 to 3000 words, okay, and if you look at it even over a few days, I will be using at least 20,000 words that are quite common, okay. They are not rare. If you hear the word, you will say, oh, I know, this is a routine word, right, but you may not say it so often. Bleak, suddenly I thought of a word. I don't know, today I don't think I use the word bleak anywhere, right, yesterday, last 3 days, right. Similarly, you just randomly say one word, most probably you won't have said that in the last 3-4 days at all, right. So, these, but they are not, bleak is not a very rare word, right. So, it's the weather is bleak or it's a bleak news, so many things you say in some context, right. So, therefore, you know, 20,000 words itself is a very small vocabulary we say. We normally, you know, say at least 60,000, 65,000, right, 100,000 is a reasonably large vocabulary that will cover most of what people say. Okay. So, therefore, suppose I am dealing with a 100,000 word vocabulary, right. What will I do? In the one hot representation, what will I do? So, first word I will make 1 0 0 all the way 100,000 cross 1, right, 100,000 cross 1, right. Second word, third word, so on. Okay. So, the 100,000th word will be 100,000th word will be 0 0 0 all the way up to the last one being 1. Okay. So, this is something that I can do. But immediately you will say, hey, it looks like very lot of waste, right, because only one guy is non-zero, all the other guys are 0. So, it is a very sparse representation, and you are going to carry this into your computer and everywhere keep storing this to recognize the words. Does not seem a very efficient way of doing things, right. So, one is that there are only one non-zero entry, which is actually unit, right, 1 in the 100,000 dimensional vector. Rest all are 0. So, it does not seem like a very efficient way of doing things. Okay. So, it seems like simply carrying a lot of zeros and not something very useful. Okay. The other thing is, if you look at apple, orange and man, right. So, if you look at these guys, right. So, what did I say? I said this is what 1 0 0, this is 0 0 1, this is 0 1 0, this is 0 0 1. These are what we call as unit vectors in the 3-dimensional space, right. So, this is like the E1 vector, this is the unit vector in the these are the unit vectors, right. So, in the 3-dimensional space. So, in 3D I can plot it now, I can plot x, y, right, x axis, y axis, z axis, right, and this point is 1 0 0, this point is what 0 1 0, and this point is 0 0 1, right. So, these are like your coordinates, 3-dimensional 3D coordinates, right. So, this is basically 1 0 0 is apple, right, 0 1 0 is orange, and this is man. So, if I plot it in this 3D plane, this looks like a this is how these points look like, this one-dimensional representation, the one hot vectors, right. So, these are all one hot vectors. Okay. So, therefore, if you look at the distance, so what is the distance between the apple and orange? So, first of all, I want to ask you, if you look at apple, orange and man, are they are apple and orange somewhat, there is some connection between them, apple and man, is there some connection, orange and man, is there some connection? If I ask you, which of these three you feel there is a strong connection between the two? If I take any two words, let us say apple orange or apple man, which is more stronger connection? You would say apple orange, because apple and orange both belong to the fruit family, right. But apple and man, okay, one man might be eating apple or something, but I do not see a very strong connection. But both apple and orange belong to the fruit family, right. Or similarly, if I look at orange and man, right, versus orange and apple, the same thing happens, right. But on the other hand, if I had father, son and Australia, right, again you see father and son, there is some relationship, right, whereas Australia, okay, father might have gone to Australia, son might have gone to Australia, but this seems to be a stronger link between the two, right. So, father and son often go together, right? A father in Australia once in a while, right? Somebody in the family might have gone, but father and son occurs in many almost all families, right? So therefore, we want some words that are closer in some sense, what you call semantically closer, some kind of meaningful connection between the words. If they are close, then we need them to be close also in some space, right? So what we are saying here is, if you look at this, if you look at what does this mean? This has, if you look at this guy, it is basically in an xy plane, right? We have this guy as apple 1 0 0. I am ignoring the third dimension. This is orange, right? If I am doing, and this is apple, if I look at the distance between this guy, this is unit vector, this is unit vector. So by Pythagoras theorem, it is 1 plus 1. So this is square root of 2. So the distance between apple and orange is basically a square root of 2, right? If I look at apple and man, so if I look at apple and man, right? So this is x and this is z. If you see, apple is 1 0 0, this is 0 0 1. Again, this is unit vector, this is unit vector, and this is square root of 2. So apple is equidistant from both orange and man. In fact, any two words will be equidistant. So if you look at orange versus apple and man, they will be equidistant. In fact, this is not necessarily only in the even if I have a 100,000 dimensional vector, right? I will have the first guy being 1 0 0 0, and the second word is 0 1 0 0 0. The third one is 0 0 1 0. All of them are 100,000 cross 1, right? 1000 cross 1. But if you look at the Euclidean distance between them, there is only one guy. 1 squared plus 1 squared is basically, and then taking the square root of that, so it is 2, square root of 2. So all words are equidistant from each other. Okay, so that's what is basically the problem, and all of them are equal to square root of 2, because it's 1 squared. Always between any two vectors, they only two non-zero values are there, and so the square of them, 1 squared plus 1 squared is 2, and then square root of 2. So all of them are, even in a 100,000 dimensional space, it's only square root of 2. Okay, so all words are equidistant. So there is no connection between any of the words in this one hot representation. So there are two disadvantages that we see. So there are lots of zeros unnecessarily we are going to carry, and second is all words are equidistant . Okay, so that's another problem. Okay, that means I cannot get a sense of are two words more closer in meaning, are two words close in what sense is always an important thing, but just intuitively what we are saying is, in language certain words have certain connection with each other, like fruits, right? Apple and orange are fruits. Immediately you see some connection between them, a very common connection, right? So are two words closer to each other, right? Here that is not there. every word is square root of 2 away from every other word, okay. They are all equidistant from each other, okay. Or if I had only 2 words, let's say yes and no, right. So that will be only a 2-dimensional plane, right. So this will be x and y. So 1 0 is yes and 0 1 is no, right. So this also, yes and no are opposites of each other, so those are also square root of 2 in a 2-dimensional space, right. So that is also what I am trying to say, okay. So how do we address these two problems, okay. So this is something that we are going to look at it.